Thank you. Thank you very much. Good morning, everyone. I'm Francesca Tonolo. I'm a postdoctoral researcher at the University of Rennes in the group of François Lick. And today I would like to show you the work that we did regarding the collisional excitation study of a PO plus molecule with the para-hydrogen, and how this work served also to to bring a contribution on the modeling of phosphorus abundance in the interstellar environments. So we decided to investigate this system for three main particular reasons. The first one is widely known. Ions are quite important for interstellar medium and for astrophysical modeling purposes, since they are quite good diagnostic tools to trace the evolutionary stage of astrophysical objects. And also they play a prominent role for chemical reactivity. Hence, we need to know in an accurate way their abundance and distribution in order to have a good knowledge of the chemical networks that are involved within them. And in particular, phosphorus deserve a particular attention since phosphorus building elements in interstellar environment are not very well understood. Phosphorus is a quite interesting element from a prebiotic point of view. It is part of the main building blocks of biomolecules, and in particular the PO bond is extremely important for this reason. But even if it was detected quite abundant also in different sources, astrophysical sources, in interstellar environment, it was not detected quite a lot, phosphorus-bearing molecules. And this could be due to different reasons. First of all, phosphorus has a high sublimation temperature, and this means that it can suffer depletion on interstellar grains. And also we have a paucity of observational data. This means that we still need to further investigate phosphorus-bearing molecules in order to understand its distribution and also the chemical networks that are involved within this element. And in particular, PO plus ion was recently detected in this molecular cloud by Victor Rivilla in 2022. And in this molecular cloud that is in the Sagittarius B2 nebula towards the center of our galaxy, where local thermodynamic approximation cannot be used in order to model in an accurate way the abundance of this element in this interstellar environment. In this cloud, the most abundant perturber is molecular hydrogen, and this is why we decided to further investigate this system from a collisional point of view. So we started from scratch, from the characterization of the potential energy surface involved for this system. We considered the two species, so target and collisional species, as rigid bodies, and we computed the interaction energies within this level of theory based on couple cluster theory, explicitly correlated, and with the quadruple zeta quality basis set. Then we fitted the potential as an expansion over angular functions. And at this point, we checked for some assumption that we could do in the treatment of this potential. First of all, as you can see here from the cuts of some of the potential energy surface with respect to different orientation of H2, that the anisotropy of the potential is quite weak with respect to the orientation of H2 with the PO+. And this means that we can safely assume that the expansion of an angular function has the main important terms in the first two angular moments of the collider. So we decided to neglect all the terms involved with the L2 greater than 2 in the expansion. This is a quite good simplification, in particular from a computational point of view, because it permits to obtain the full treatment of the potential by simply computing 5 orientations of H2 with respect to PO+. This is the full dimension potential, but we also decided to check the validity of another strong approximation, the spherical average approximation. This neglects the internal structure of H2. And in particular, in this way, it's possible to characterize the potential by simply averaging different orientation. In this case, the 5 orientation that we computed before, by simply averaging these orientations. And but obviously this approximation needs to be validated, and so we did it by checking the discrepancies that we had in the cross-sections values with respect to the 2-dimensional potential and the full 4-dimensional potential. The average absolute percentage deviation that we found was quite small, in particular for astrophysical purposes that we are going to that we want to pursue. And so in this way, we decided to continue within this spherical average approximation that indeed has a very strong simplification on the computational cost. Another check that we decided to do is to see how the orthostate of hydrogen was affecting the cross-sections, the inelastic cross-sections. Indeed, in the cloud that we would like to, we wanted to model, the temperature are relatively high. And so in this case, the J=1 state of hydrogen could have an impact. But as you can see also in this case, the average absolute percent deviation was quite small, and so we can safely treat the hydrogen in its J=0 rotational state to have a good modeling of the collisional behavior of this species in the environment we wanted to investigate. So we went on with the close coupling calculations, and so by treating with the partial wave function on top of the potential that we computed, and we obtained the scattering matrix, starting from which we can have all the collisional information of the system, among which also the inelastic cross-section here highlighted, and for which I'm here showing some trends with respect to the kinetic energy. And by simply averaging this cross-section over the kinetic energy, we could obtain the state-to-state rate coefficients. Here I'm showing just a few of them, and as you can see here, the trends in particular in the short range of temperature is changing quite a lot. So it means that it depends quite a lot on the temperature, and so we really need these kind of coefficients to predict this kind of behavior. In total, we computed the first data set of collisional coefficients for this system and for the 20 lowest rotational levels of PO+, from 5 to 200 Kelvin. And we hope this could be useful also for further investigations of the modeling of this ion in space. And a particular attention needs to give to this comparison here, since we already had the rate coefficients with the helium collider. And as has already been said previously, in this case, and this is quite often with small ions like PO+, the helium is not able to serve as a proxy of hydrogen for state-to-state rate coefficients. As you can see here, in particular in the low temperature ranges, the discrepancies are quite large, and in particular also the propensity rule are totally reversed. So at this point, we decided to continue with the modeling of the abundance of PO+, taking in account this data set of coefficients. The molecular cloud where PO+ was detected has quite particular conditions, is characterized by very low densities of hydrogen, but high kinetic temperature. This means that the local thermodynamic equilibrium approximation cannot be used, but we have in most of the cases a kind of quasi-thermalization condition. This means that the distribution of the population among the levels can be modeled within only one single excitation temperature. And this can be a good approximation, but needs to be validated. So since we had the previous modeling within this quasi-thermalization condition, and we have this new data set of coefficients, we decided to compare the efficiency of these. So we perform radiative transfer calculations on top of the two detected lines. Here, the third detected lines is obviously is impacted by other transitions, so we could not use it. But we decided to plot here the ratio of intensities of the two first rotational lines of PO+. In red, you can see the observed ratio. And in this way, we were able to constrain the density of hydrogen in this cloud. The kinetic temperature, in particular in this range, is not very well constrained, and this helped us to have an accurate value of the density of hydrogen for this cloud, starting from which we were able to obtain within a single transition analysis the column density of PO+ in this source. This column density resulted to be a factor of 60% smaller than the previously local thermodynamic equilibrium derived value, which is a good difference, but not as much for astrophysical purposes. So we can safely say that also in this case, the quasi-thermal equilibrium was a good model for this kind of environment. But if we look at the behavior of the excitation temperature with respect to the column density of hydrogen for different kinetic temperatures, we can say that strong Maser phenomena are shown. And this means that if we want to model sources with higher densities of hydrogen, we really need this data set to have accurate predictions and accurate modeling of abundances. And thus, we really hope that this new data set could help for future detection and future prediction. So I'm just concluding saying that here I presented the collisional investigation that we did for this system, starting from scratch, starting from the characterization of the potential, and on top of it, we performed the scattering calculation to obtain the first data set of collisional coefficients for this system, and then we continue with the astrophysical modeling to refine the abundance of PO+ in the cloud where it was detected, and we hope it could help also future detections and future investigation of this molecule in space. So I will thank you all for your attention, and a particular thank to my group and my collaborators that helped me quite a lot for this project.